Hi, everybody. Welcome to what I think is the fourth webinar now in our Task Team 3 webinar series. So this started out with sort of a focus on salinity feedback effects on AMOC, but I think at this point we're going to open it up and invite presentations from the task team on any topic to try to keep this going through this year to get to our next AMOC Science Team meeting, which will be next May, I believe. So feel free to email myself or Wilbert if you'd like to present any of your current work and have other people respond to it. So we're delighted to have Tom Delworth give us a talk today, and I'll let him start.
Okay, great. Am I off mute?
Sounds good, Tom. Go ahead.
Okay, great. Thanks very much. Very happy to be able to have a chance to show some results here, and be very anxious to hear feedback and any comments everyone might have. So the point of this work is really to, within a somewhat idealized framework, try and examine the role that the NAO plays in a little bit in orchestrating some of the variability we see in the Atlantic, but then perhaps more importantly, its impact on the larger climate system. So we want to develop or run a set of experiments with a suite of models that really try and isolate this question. We obviously see that the NAO is a dominant mode of atmospheric variability, and we see its impact on the atmosphere, and there are a number of work showing its impact on the ocean. But what we try to do here is to examine the NAO's impact on the ocean, and then how that signal feeds back onto the atmosphere and imprints itself on hemispheric and perhaps even global climate. So that's the goal here, is really exploring the role of these NAO variations and driving AMOC and ocean heat transport variations, and then their impact on the broader climate system. So our very simple framework we're trying to adopt here is a schematic of the Atlantic and the North Atlantic current, and we're examining the impact of these winds associated with the positive phase of the NAO, or negative phase, in which they're sweeping across the subpolar gyre and extracting more or less heat in a positive or negative phase of the NAO. And we want to see how does that impact the ocean circulation within a modeling framework, and then how do those changes in the ocean impact the rest of the global climate system. Of course, this heat transport system extends all the way into the Arctic, and one might expect that this could therefore have some impact on Arctic sea ice, and we'll see that within this modeling framework, it does indeed have that sort of impact. So we're doing this within a modeling framework. Hard to do this within a purely observational framework. And this is the basic framework that we'll use. We have on the left baseline experiments, and on the right perturb experiments. And all the experiments shown here use fully coupled models. Schematically, we have an atmosphere on top and an ocean below, and they talk to each other by exchanging air-sea fluxes of heat, water, and momentum. And so the two models, either the baseline experiments or the perturb experiments, are precisely the same, and they only differ by one feature. Here in the perturb experiments, we intervene at each model time step, and we input into the ocean an extra bit of heat flux. And that extra bit of heat flux has a spatial pattern of the NAO. And so by systematically imprinting onto the ocean an NAO-related heat flux pattern, these perturbed experiments feel a particular phase of the NAO that the baseline experiments do not. And so that's the difference between these two. So we're pushing the ocean, making it feel a particular phase of the NAO on these perturbed experiments that we do not do on the right side, or the left side, the control experiments. In each case, we run an ensemble of experiments in order to get a better signal-to-noise ratio, because we're still computing the regular air-sea heat, water, and momentum fluxes here. So we have all the normal couplings going on. It's just that we're always pushing slightly the ocean towards a particular phase of the NAO. We do experiments with several different models. We do experiments in control simulations where we have constant radiative forcing. We do simulations with changing radiative forcing to look at the impact on historical simulations. So we do use multiple models for these studies. There are 4 GFDL models that we use here. There are a variety of atmospheric and oceanic resolutions, going from 2 degrees down to ½ degree in the atmosphere, and from 1 degree to ¼ degree in the ocean. To first order, the results are fairly robust to the particular model we use, because I think that's based on very simple physics, the process going on. So we'll show a lot of results. Some of them will be multi-model means, but the results are fairly robust across these different models. So this is the spatial pattern of these heat fluxes we're applying. This is derived by computing at each grid point a regression coefficient between the heat fluxes coming at each grid point over the North Atlantic as estimated from the ECMWF reanalyses. We're regressing that versus a time series of the observed NAO index based on a station index between Iceland and the Azores. And we're applying this particular heat flux pattern only in the months of December, January, February, and March. That's when the NAO index is defined. So we have this spatial pattern. This corresponds to a positive phase of the NAO. Blue indicates enhanced flux of heat from the ocean to the atmosphere, and orange vice versa. And the integral of this heat flux is constrained to be 0. We only apply the heat flux over this region of the Atlantic into the Barents Sea and Greenland Seas. The rest of the globe is still part of the coupled model, but we are not applying any extra heat fluxes. And the integral of this heat flux is constrained to be 0, so that we're neither adding or subtracting heat to the entire coupled climate system. We're just simply rearranging that. And so we do a number of different simulations. We can do various flavors. One simulation I'll show first is this. We simply, from a long-running control simulation, we fork off an ensemble of perturbed simulations in which we suddenly switch on a positive phase of the NAO, shown by this heat flux, and leave it on, sort of study the adjustment problem. Other experiments are in which we can vary sinusoidally these NAO flux forcing. So we let control models run along, we fork off perturbed experiments, and we impose a sinusoidally varying NAO forcing with a wide variety of periods. These are all separate ensembles of experiments with NAO forcings of 2 years, 5 years, 10 years, 20 years. And there we're examining the sensitivity of the climate system to the time scale of the NAO forcing. I won't show those results here, but these results show that the climate system is far more sensitive to low frequency variations of the NAO than to high frequency variations. I think there's some important feedbacks. And also we do simulations in which we impose a varying NAO forcing that is scaled to the observed NAO over the 20th century to look at more realistic situations. So here's a very idealized case in which we do a switch on of this NAO forcing. So we turn this on and leave it on. We scale it by the interannual standard deviation of the NAO. So the forcing is 1 standard deviation on interannual timescales. And shown on these 2 left columns are the responses of the model to those imposed changes. So the rows indicate time in years after we turn on this extra NAO forcing. The left column is the AMOC response, and depth on the y-axis and latitude along the x-axis. And the right column shows the change in meridional heat transport, shown here, where red indicates enhanced northward heat transport. So looking at AMOC, we see a decadal scale spin-up of the system to this imposed switch-on of the NAO forcing. Locally, the response starts in the subpolar gyre, expands into the subtropics. We see a consistent change in meridional heat transport, very little signal here, and then gradually these red colors propagate southward associated with enhanced heat transport. You can see a lot more of these in a Journal of Climate paper published a few months ago now. So we can move on to other cases. For example, we have many cases in which we apply a perfectly sinusoidal forcing of the NAO to study the response of the system. So shown in the top panel here, the x-axis is time in model years, 100 model years. The y-axis is latitude from 80 north to 30 south. And what we're showing is the response of the AMOC to a perfect 50-year periodic NAO forcing. And so the color shading here is the ensemble mean AMOC in the models with the NAO forcing minus the ensemble mean AMOC in the models without the NAO forcing. So this is the response. And this plus minus shows schematically the phase of the NAO. So this is a NAO maximum here with strong winds extracting heat from the subpolar gyre, and negative is the reverse. So over this 100-year period, we have two peaks and two troughs of the NAO. And so in response, we see these very, very clear spin up of the AMOC with southward propagating signals in each case here with amplitude of several spheroidrips, so the amplitude in spheroidrips. But since we're using coupled models now, we can move beyond the oceanic signal to look at how this then imprints itself on the atmosphere and the larger climate system. And remember, we're not adding or subtracting heat to the climate system. We're simply rearranging those fluxes in the North Atlantic. So shown in the bottom panel is the response of northern hemisphere mean surface air temperature now over the region 23 north and 90 north. So these are the differences again, the ensemble mean air temperature with the NAO forcing minus the ensemble mean without the NAO forcing. And so we can see in response to this enhanced AMOC, we're transporting more heat poleward, and we actually warm the entire hemisphere. So this is the amplitude of the warming in degrees K. So we have a couple tenths of a degree warming here, and the weakened AMOC leads to a couple tenths cooling and so forth. So we have this very clear hemispheric scale temperature response in response to this NAO forcing, which changes the AMOC zone. We're bringing more heat poleward. But an important component of this is we're not only bringing heat poleward, but feedback processes operate at high latitudes. So as we bring the heat poleward, we melt sea ice, we lower albedo, and a very important piece is that we increase the net absorbed shortwave radiation. So we warm both the ocean and the land, reduce snow cover, darker surfaces absorbing more solar radiation, and we actually reduce cloud cover as well. So this positive shortwave feedback is a real important player in the hemispheric scale response of the climate system here. So we can move from these very idealized cases, either switch-ons or sinusoidal forcing, to look at the 20th century and the impact of the NAO, or an attempt to estimate the impact of the NAO on the climate system through its influence on the ocean. So the top panel shows the observed NAO index over the last 130 or so years. This is the Harel station-based index for the winter season, Northern Hemisphere winter season. So blue indicates that negative NAO, and red is positive. So we see the late 20th century, this very strong negative values ramping up into the 90s, coming back to more neutral values over the last decade. Over the last few winters have had some positive peaks. So we take this last 60 or 70 years of the NAO and apply that forcing to the model using the same spatial pattern that we derived before, but simply taking that spatial pattern and multiplying it by the year-by-year variations of the NAO and imposing that on sets of models. So we have ensembles of models with this forcing and without. And now we're using model simulations that include the time-varying radiative forcing over the 20th century. Both ensembles do, they just differ by whether or not they include the NAO forcing. So here then is the multi-model. We combine three different models here. This is a multi-model AMOC response to this NAO forcing in these models from 1950 to 2015. The y-axis is the amplitude, so blue indicates a weakening. The width of this is some measure of the spread in the different models. Bottom line is, in response to this negative NAO in the 60s and early 70s, a strong weakening, moderate weakening of the AMOC. And as we go into the 90s and 2000s, this ramp up, and we've seen this certainly in a number of simulations before, this strengthening the AMOC, and then subsequent weakening after that. But then again, since this is a coupled model, we explore the other implications of that, and one of these is for Arctic sea ice extent. So this panel shows on the top for September the change in the aerial extent of sea ice relative to the 1979 to 1990 base period, since that's when the satellites came in 1979 over this period. But the models, of course, simulations start in the 1950s. These green bars indicate the relative change in sea ice extent in the models that have radiative forcing and the NAO forcing. And the brown bars with the red symbols in the middle indicate sea ice response in the simulations with only radiative forcing but not the NAO forcing. And the bottom panel shows the difference between these two, and the blue line shows the observations over this period. So obviously a very strong decline in sea ice area is clearly dominated by the radiative forcing signal. That's pretty clear. But riding on top of that radiative forcing signal is an extra sort of multidecadal variability, at least as simulated by these models, that is a response to the AMOC, a weakened AMOC here leading to enhanced sea ice area extent, a strengthened AMOC leading to reduced sea sea ice area extent in the Arctic over this period for September. This then we can now also look at surface air temperature over the hemisphere as a response, again this same period, and this is the response to the NAO forcing impacting the ocean, impacting the atmosphere then, and so a cooling in the 60s and 70s of order 0.1 to 0.2 degrees over the hemisphere, a subsequent rapid warming associated with the AMOC strengthening, again about 0.2, and a ramp down since then, all in response to the NAO. And one of the more interesting things is, since we use coupled models, is that we can look at other interesting features. And one of the coupled models we use has high enough spatial resolution to begin to marginally resolve tropical cyclones. We actually use this model in quasi-operational seasonal predictions, and it actually has skill in tropical cyclone and hurricane prediction in the Atlantic. So it's a credible model for this sort of study. So in that model, in those simulations, we can compare the distribution of tropical storms when we include the NAO forcing versus when we do not include the NAO forcing. So what we're plotting here is a histogram or distribution of the percentage difference in tropical cyclone activity in this latter period minus the earlier period. And so the zero line here means no change. And we're building this distribution by Monte Carlo resampling of our simulations. This black line is from the experiments that are labeled HIST, just historical relative forcings. They are symmetric, or are basically symmetric around zero, suggesting very little impact in this model simulation of relative forcing on the changes in the distribution of tropical cyclones before and after. The red line, however, is shifted clearly to the right, and that's the change in distribution when we include the NAO forcing. So the enhanced heat transport warming of the hemisphere by this NAO forcing and AMOC spin-up in this model has shifted the distribution to the right and has a tendency for more tropical cyclones, more storms over the Atlantic sector in response to this. Of course, the blue line is way out here. That's the observations, and we clearly are not recovering all of this. There's a lot more to the story. This does suggest that the multidecadal NAO forcing impacts the ocean in such a way as to create atmospheric conditions more favorable for tropical storms. And through additional analyses, we show that that actually is due to, or at least related to, changes in the vertical shear of the zonal wind in the tropical Atlantic as a response to this hemispheric scale warming. So let me just conclude that these NAO, we're trying to evaluate the impact of NAO variations only on the ocean, not the direct impact, which we know is large, to the atmosphere. We can show through these model simulations, one estimate at least, is that these NAO multidecadal variations drive multidecadal change in the AMOC, which then impact hemispheric conditions by driving more heat poleward and by invoking these very important shortwave feedbacks over the Arctic that are very, very important. These NAO-induced variations are clearly, say, over the Arctic, in addition to the dominant anthropogenic forcing trends. These are multidecadal variations that are riding on top of this. But it's very important for things like tropical cyclones and other factors. So some of the key challenges, we've taken this NAO forcing as a given here, but what generates this multidecadal NAO variability? Is it simply white noise? Or is it something more complicated? Is there a role for feedback? Is part of this a response to relative forcing? Lots of interesting questions there. And then how widely do models differ in the response to the NAO? If you apply these NAO forcing in different models, I'm sure there's going to be a different response, and how sensitive is that? And how do we know which models are better? What should the response be? I don't think we know that. And what are the underlying mechanisms determining that? So I think what we want to suggest here is that there are many factors playing a role in the low-frequency change in the Atlantic, including aerosols, greenhouse gases. Those are all really key players. But in addition to that, these multidecadal variations of the NAO, I think, are driving a very key component of the multidecadal variability that we see in the observations over the Atlantic and extending over the hemisphere. So I'm going to conclude with that.
Great. Thank you very much. I'm going to go ahead and take everyone off mute right now.
The conference has been unmuted.
And we'll go into some Q&A. I saw a few hands shoot up, so let me call on some folks, and then, of course, people feel free to chime in and introduce yourself if you don't. Paula, I saw your hand go up first.
Okay, thank you. That was a very nice talk. I just have two questions, just a clarification. You showed the pattern of heat flux that you applied, but you changed also the momentum flux, or was it just the heat flux that you changed?
So we've done a lot of mix and match experiments. The experiments that I showed only changed the heat flux.
Okay.
We have done additional experiments in which we changed in addition to or in place of the water flux as well as the momentum flux. On these time scales, it looks to us in these models that the heat flux is really dominant. However, certainly on the shorter time scales, adding in the wind stress is pretty key. So we've redone exactly these 20th century experiments in which we also put in the momentum flux, and we get pretty similar results. So I think for those long-term changes, the heat flux is really dominating.
Yes, and the other question that to clarify that I had that you, of course, you focused on the temperature, air temperature differences in the northern hemisphere, but given the feedback on the ice, the suggestion is that this would actually, even though diluted, if you look at the global change, it would change the global temperature or not?
Well, that's an interesting, certainly question. So one of the interesting things we see is we actually see an interhemispheric asymmetry. So as we systematically apply these NAO fluxes and warm the northern hemisphere, we do see a response in the high latitudes of the southern hemisphere, broadly speaking, a bit of a cooling. So there, and we think that there are two pathways for that. One is atmospheric and one is oceanic. But on the short time scales, it's clearly an atmospheric pathway. And so we see some change in the tropics and then some change in the zonal winds in the southern hemisphere. It's a modest signal, but these are coarse resolution models, but it's an intriguing signal. So the overall effect is still, if you average out over the globe, is still a bit of warming. And I think it's a bit of warming because of these feedbacks that come in, the shortwave feedbacks coming in. To zeroth order, you're redistributing heat, but we're also increasing the total amount of absorbed heat through these feedbacks.
Mm-hmm.
Great, thanks. Wilbur, did you have a question?
Yes. This is Wilbert. I have one question about the methodology, and that is the fact that you apply this surface heat flux anomaly to the ocean. But are you applying a similar but opposite heat flux to the atmosphere? So is the atmosphere feeling that heat flux as well?
Yeah, no, we are only. It's a fictitious thing you can do in models, but we are only touching the ocean. The atmosphere feels. The only thing the atmosphere feels is if the ocean changes as a result of this, then the atmosphere feels that, but there is no anomaly applied directly to the atmosphere.
Okay, right. And another question that I had is, is there anything you can say about the Atlantic multidecadal oscillation as like a metric of sea surface temperature variability in the North Atlantic?
Well, I guess part of implicit in this is that it's an onion and how many layers you peel back, and so I'm starting with, given these NAO fluxes, we can drive variations in the Atlantic that look to some degree like the observed AMO. I think there are more things going on. Mm-hmm. So in some sense the question then is, why are we having these NAO variations in the 20th century? Is that simply white noise? Any white noise series has some periods of enhanced multidecadal variability, or are there other processes going on? And I don't know about that. I think that, so I'll just leave it at that. I don't know what is driving that NAO forcing. It may simply be white noise.
Well, where is the white noise coming from, though? I mean,
well, there's white noise in any system, I think. And
yes, no, but I mean, since you're talking about the atmosphere, normally you think, for the ocean that the atmosphere has many scales and you apply white noise. But now we are talking about the coupled system. So what is providing the coupled system with white noise? Is it not in the astronomical signal? So I just think to say white noise without it, I don't see where it would come from in the coupled system.
I guess I don't understand the question. I don't know how you could not have white noise in the system.
Well, the white noise has to be internally generated by the
Exactly.
Well, then, exactly. So, and the component of the white noise that excites the low frequency is the low frequency one. So you're saying the system is forced by internal low frequencies, and that's exactly what you're trying to establish why they're there in the first place.
Well, I would say that, one, I don't know where the NAO low frequency variability is coming from in the real world. I think that the right null hypothesis to me is that it's driven by atmospheric processes. And then to me, the burden of proof is on to show that it's something more than that. So even if you take a purely atmospheric model and you run it, you will get multidecadal you'll get white noise variability in the NAO, which has some projection at long time scales. And I think there have been studies that have shown that even if you take that level of white noise, that will excite lower frequency modes in the atmosphere. To me, the real interesting question then is beyond that, does the coupling from the ocean alter the spectrum of that variability, or do the relative forcing changes alter the spectrum of that variability? I think those are the interesting questions.
Michael Ball, did you have a question as well?
Yes, it looked like the MOC anomalies were largely contained in the subpolar gyre. So the upwelling at sort of roughly the boundary, I think, the subpolar and subtropical gyre. Have you looked at that? Is that an adiabatic shoaling of the thermocline, or do you know what the anomaly looks like in 3 dimensions?
In 3 dimensions, I'm not quite sure. I don't think it's adiabatic. I think there's a lot of diabatic process going on here. But if we look at this particular slide, I mean, the anomalies start out in the subpolar gyre, but do extend all the way into the southern hemisphere. So there is a pretty wide latitude.
I was thinking more of the 100-year time series, where you had 50-year periodic forcing. Yeah, I mean, it looks like the second 50 years, maybe things have penetrated a little further south than the first 50 years, but at 40 north, there's a lot of stuff coming back up again.
Right, I think you're exactly right. I think there is a lot of recirculation in that signal. Now, these, I'm pretty sure that these were calculated in density space too, so I don't think that's an issue. But yeah, okay. It's stronger in the subpolar gyre, that's for sure.
Great. Are there any other questions for Tom?
Yeah, Tom, I had a question about the cyclone plot that you showed, and I'm wondering if that's related to an SST signal in the tropical Atlantic.
Well, that's a very interesting question. I mean, our model, as I think many, has a pretty weak change in the tropical North Atlantic SST in response to a spin-up of the AMOC. I think that may be part of it. I think potentially a larger, and another piece, though, and it's hard to tease these out, is a more hemispheric scale change in the structure of the winds. If in our Journal of Climate paper, we show a lot of figures, and one of them we show is the change in winds as a function of season in response to this warming or cooling or spin up or spin down of the overturning. And we see pretty strong coherent change in the westerly winds over much of the hemisphere in response to this strong high latitude, or moderate high latitude warming. And so I think it's that change in the winds which results in a reduction of the vertical shear of the zonal wind extending from South America all the way over to Africa, right in the key heart of the tropical cyclone development regions. My guess is that that's key, and how much of that is coming from local SST versus the more hemispheric scale pattern, I don't know. My intuition is the hemispheric scale pattern is really integral to that.
Great. Is there any other last minute questions? We are running about 30 minutes, which is our ideal time for these. Okay, I'm going to take that as no. Thanks everyone for tuning in, and a big thanks to Tom for presenting today. Really nice presentation. I was recording these, and I know a number of task team members always like to watch them afterwards because they can't tune in. So I'll get this shared and let everyone know when it's online.
All right.
Thanks very much.
Thank you very much.
All right. Thanks a lot, Tom.
Thanks, Tom.
Thanks everyone. Bye.
Thanks everyone. Bye-bye.